page 4 of the computer system notes, and this is section 3 on memory access. And the text reference here is section 3.3. So we've talked about how memory is made. Now we'll talk about how issues associated with processors accessing that memory. So first of all, memory is treated as an array of bytes, and it's addressed by the byte. So you start at byte 0 and you go on. So memory is byte addressable. And next point is when so if you want to access one byte, you give this the byte number. What if there's multiple bytes of it? You usually give the first byte number, and then, so say you're reading 4 bytes from memory, then it will give you that first byte plus the 3 following it. But the question is, what order is that multi-byte data stored in memory? And there's 2 options. So multi-byte data order. So let's just start with an example. So when I write a hexadecimal number, I'll preface it with 0x. And to write a 32-bit number, or that would be 4 bytes, because there's 8 bits per byte, that would be 8 hexadecimal digits. And I've spaced them out just to make it clear, like each pairing of hexadecimal digits is 1 byte. A hexadecimal digit represents 4 bits, or takes 4 bits of storage. And so the first byte in the number is the MSB, which stands for most significant byte, and the last byte is the least significant byte. And just to emphasize, this whole thing is 32 bits, or 4 bytes total. Alright, so if we're going to store this in memory, the question is, do we store the 1, 2 at the first address and the 3, 4 at the second address, or do we store the CD at the first address? So for that second option, you're storing the least significant byte at the lower address, and then the next least significant byte, the AB, would be at the next address, and so on, which might seem logical, but it's also a little harder to read from memory in that order. When you're looking at memory contents, which you sometimes do in a course like this, it's easier to read if it's if you've got the 1, 2 at the first address and the 3, 4 at the next one, so then it it flows left to right instead of right to left. So there's names for these 2 orderings. So big endian order looks like this. So let's just say we've got memory here. You're going to represent it as an array, and just going to represent the first 4 bytes. I'll number those 0, 1, 2, 3, and with big endian we put the most significant byte first, 3, 4 next, A, B, C, D. And when you read memory contents, usually they're arranged like in a row, left to right, so you'd see that number as it appears above. The other option, I should have a dash there, that's big endian, and the other is little endian. So we have CD, AB, 3, 4, 1, 2. And those are the byte addresses there. So the name big endian and little endian comes from actually from Gulliver's Travel. So there was debate, I would say, it was either the 70s or the 80s they were debating, which is the better order to store this data in memory, and it turns out it's not really very important. Some processors let you do it either way. So when you store a 4-byte value from a register into memory, so the processor will be configured to always do it one way, but some processors can be configured either way. x86 processors, I believe, are little endian. ARM can be configured either way in the lab. It's little endian. Trying to think of some big endian processors. So the Motorola 68000, that's a processor that was used it was used a fair bit, and one of the notable places was in the first Mac computers. So anyway, in Gulliver's Travels, if you've read it, I started it, got bored, and didn't finish it. But anyway, Jonathan Swift is the author. So the protagonist gets shipwrecked or marooned on this island, and there's these little people there, starts out being tied down by them, and there's a war between the two tribes, and there's the big Indians and there's the little Indians, and what they're warring about is which is the correct end of a soft-boiled egg to chop off. Do you open it at the little end or the big end? So if you look carefully at an egg, you'll notice usually there's a narrow end and a wide end. Okay, so next we have alignment. So just first of all, multi-byte accesses are specified by the address of the first byte. So if you're reading a 4-byte value, as shown in these two diagrams here, you would use the address 0, and it'll give you bytes 1, 2, and 3 as well, if you're loading 4 bytes. So there's some processors require that if you load a 4-byte value, it starts at an address that is a multiple of 4. If you load a 2-byte value, it needs to be a multiple of 2. If it's a 1-byte value, well, it can be at any location. And so this concept is that they're naturally aligned. For example, for a 2-byte load, a load is just reading from memory, the address must be a multiple of 2, and for a 4-byte load, the address must be a multiple of 4. And if you don't follow that rule with a processor that requires it, then you'll get a bus error or a memory error. So you'll generate a hardware exception, and your program will more than likely be terminated. So the processor that we're using in the lab is an ARM processor, and it requires that that multi-byte accesses be naturally aligned. A notable exception to this is x86 processors, where you can start any size data, load, or store at any address.